this talk will be given by Aritra Dar from ETH Zurich. So I think this is really interesting work because it provides a really good security guarantee even in a very challenging situation. And let's welcome our speaker.
Yeah, thanks for the intro. So I'm Aritra from ETH Zurich. We're going to present our work, ProtectIOn, root of trust for I/O in compromised platform. So let's think about medical implants that can talk to internet. Yeah, it does sounds very scary, but medical implants such as a pacemaker and insulin pump that could connect to internet and retrieve some parameters are available commercially. And typically doctors use some browser-based application to access such devices remotely. And these applications are all running on commodity hardwares, right? So you are running operating system and browser, JavaScript engine, and all of them are running millions of lines of code. So typically you have a very large attack surface. So an attacker who can compromise the host anyway, so it could be a software attack or it could be hardware attack. So this attacker could not only see these input parameters, but can also introduce arbitrary changes, which could be really disastrous. So to deal with this problem, we already have an idea of remote trusted path. So remote trusted path says that through the trusted I/O devices, the user can talk with a remote server through a compromised host and compromised network. And at the end, you're going to have some guarantee. So the guarantee in form of I/O integrity or I/O confidentiality. So let's look a little bit more details into some of the past works, and let's try to see how you can build better systems. So one way to preserve integrity is using transaction confirmation devices. As the name suggests, transaction confirmation device gives you a preview of the input parameters in a second screen. So the second screen could be, for example, a mobile phone. However, you can now see some of the problems here. So transaction confirmation devices works really well with your bank transaction, but it could be a huge problem if you have a very complicated UI. Moreover, in a stressful scenario, transaction confirmation device has a problem with user habituation error. So at the end, these things not really give you good user experience. So can we do better? So there are some works based on input signing. And the idea is pretty simple. You have a small trusted embedded device that is connected to all the I/O specifically the input devices, and connected to the host. And it takes all the textual input, sign them, and send them to the end system. And the end system checks whether the signature are valid or not. If it is valid, it accepts all the input and program themselves. Now it looks like a pretty good idea, but apparently we can attack them very easily. So think about the doctor want to put the insulin pump level at 177. The attacker shows you 17. So user thinks, maybe I forgot to put 17. So how about I put another 7? So now the embedded device, it records 1777. And attacker shows you 177. Everyone is happy. But at the end, user sees 177, device records and sign 1777, and host finally sent 1777. And you can easily do this attack also in the other way. You can drop arbitrary characters also. Papers like integrity key actually is vulnerable to such kind of attack. So from here, we can derive our first observation, what is missing. What is actually missing is the output integrity. So the device has no idea what user is actually seeing on the screen. So if you have no way of defining output integrity, the input integrity cannot be provided. So can we do even better? We can do a little bit better with overlay. So there are several papers that talk about overlay. How it works is that you, again, have some kind of trusted embedded device that sits between all the I/O devices and the host, and which gives some kind of overlay. So overlays are on this textual box, which is in green. So user can see and program these parameters that attacker could not see or manipulate. So apparently it looks pretty good, but it has some other problem. So for example, the attacker could change the non-protected part of the screen, which sounds like not really a huge problem, but it could change the user's perspective. For example, the insulin and heart rate, these two could be interchanged, and the range of these two parameters are very overlapping, right? And for not only that, you can change some unit. For example, you can change the deciliter to cc, and you suddenly boost the input by order of 100. And this could actually leads to disaster. So what we learned from this attack is, even though you are giving some sort of protected output, but if the output gives completely out of context, this output integrity doesn't make any sense. At the end, you are not gaining any input integrity. And the last attack that we saw, we are naming it as early form submission attack. So this is because most of the paper that try to solve trusted path, they mostly support only one input devices, namely keyboard. And it looks like supporting just one input device and leaving out rest of them may be a functional limitation, but it actually a security problem. Suppose this insulin pump again, so this is currently in focus and you want to put 177. So you write 17 and operating system just trigger a mouse click on the program button because the operating system is actually compromised. So you can actually influence, and you can do this very fast so that user doesn't have any idea that this kind of event actually taking place. So you can actually violate output input integrity. There are papers such as Fidelius or FPGA-based trusted overlay which are attackable, not only this but also the previous attack. So what we learned from here is that if not all input modalities are protected, none of them actually individually could be protected because they can influence each other in very complex way. So from this observation, we derive some requirement in order to provide a trusted path. What are these requirements? One thing is interdependency between input and output. You need to protect all modalities of input. You need to provide low cognitive load, because if you stress user to look at so many different input parameters or security indicator, most probably he will make a mistake. And of course, low TCB and deployability is one of our major factor, because what we are looking for is not to put your trust into operating system or large browser, but to really small code bases. So from here we get our idea ProtectIOn. They are built on this requirement. So how it works? So we introduce a small device, we are calling it a IO hub. And the design of the IO hub satisfies one of the requirement, that is low TCB and fast deployment. How? IO hub doesn't run any commodity or operating system. It doesn't run any browser, JavaScript engine. It does not use any hypervisor. So it uses very small code base which could be formally verifiable. And the second property is the all sort of input modality. How? We are connecting all our input devices through this IO hub. So all of our input would be intercepted by this IO hub. There would be some signature would be in place. I will go into that later on. And not only that, your output devices would be also intercepted by the IO hub. By this, the IO hub control all user interactions. And of course, just to remind you, the attacker model, all of our end systems are trusted. Of course, your monitor or your input devices has to be trusted. The remote system is trusted. In between, everything could be untrusted. The second part is simultaneous I/O. And the simultaneous I/O could be protected by overlay generation. How? So suppose the developer can say one or maybe more than one input boxes are critical. For example, here all of these input boxes are very critical, and he could actually sign this input form, and that would be presented, that would be encoded in a form. So for example, one encode could be QR code, which we are using in our current implementation. And when this QR code is intercepted by this small device through the HDMI, it could overlay the signed UI. Now, as the UI is signed, any kind of modification on this UI would be readily detected by the device. And now, how the input is handled? So, as all the input devices are connected, all modalities of input devices are connected to this small IO hub, it also overlays the mouse pointer, because of course this is an overlay on the HDMI frame. So, actual mouse pointer would be overlaid. So, you need to redraw the mouse pointer. And users started to giving their input parameters. When the input parameters are gone, then you could program it, and all of this input session would be recorded by the device and it would be signed. So at the end, you get a signed transcript, that would be sent to the remote server. So by this way, simultaneously input and the output could be protected. Now the thing is that whether this is the best thing you can do. The answer is no, because we are still leaving out a large part of the screen which could be still controlled by the attacker. So the way you can do is that you can grabbing user attention, and there are several existing ways you can grab user attention. For example, say attacker flashing some sort of malicious advice on the screen, say put 1 in front of all the inputs, right? So one of the way you can do that using lightbox. Lightbox kind of grays out rest of the part of the screen and only focuses your attention to a very small part of the screen which is kind of sensitive. You can use highlight. You can use freezing, which kind of freezes all the activities on the screen and only preserve the activity inside this small part of the screen, or which could be combinations. I would say to go to the paper, because in the paper we talk about the several kind of situation, and all of these different methods could be encoded inside the QR code that we show. So based on the specification, you can engage one or different kind of such input attention grabbing sequences. And of course, there is a way to know that when to engage this mechanism, because now as the mouse pointer is also controlled by the small device, we need to track the mouse pointer, because we need to know when user is entering to this secure overlay or user is when exiting. So for that, we basically track all the mouse pointer, and we kind of overlay the mouse pointer on top of it. In any case, attacker want to move the mouse pointer to different position, we can able to detect it, and we are doing it by doing some small image analysis. So we implemented a prototype of ProtectIOn. So we use really off-the-shelf hardwares like some Arduinos and some Raspberry Pi. And this part is, so with the Raspberry Pi, we have this small HDMI interceptor that could intercept HDMI frames and could analyze it. And now if we see the code base, let's look at the code base of the operating system browser. So you can see that, for example, Firefox or Chrome, there are over 20 million lines of code. Linux kernel is 36 million lines of code, and now Ubuntu and Arch, that's only the operating system code without the kernel. And if we see our code base, the HDMI interception overlay, everything could be done. We did it only in 2,000 lines of code. CryptoStack was implemented around 3,500 lines of code. USB stack, we wrote it from the scratch, which was around 893 lines of code. And only the big part of the code was running on the Raspberry Pi. We are using a custom kernel. We modified it and able to do it only 121,000 lines of code. But remember that you could completely skip that part and implement all of this inside a small FPGA, and the code base would be much smaller. So you can, of course, get away with that. And now question is that, well, we are doing all this analysis, what is the cost? Apparently, the display latency was only about 21 milliseconds in a full HD frame. So we can able to achieve around 46 frames per second, which is respectable. Mouse and keyboard latency in order of microseconds, so you wouldn't notice anything. And the pointer detection was around 99.7% accuracy, and we missed only the part where the pointers were a corner of the screen, because we are using very simple template-based image analysis. So this is a very layman approach. One could easily improve on that. So to conclude the talk, we look at existing research. We kind of investigate what people have done before us, and we found some drawback. And based on this drawback, we found some observation, and from there we draw our requirements. What are the basic requirements are required in order to produce a secure trusted path. And based on that, we design our system ProtectIOn. We implement a prototype which works satisfactorily in the real world. Of course, it could be improved easily. By saying that, I would like to conclude my talk. Thanks for attention. I would be up for questions.
Okay, questions from the audience? Okay, we have one.
Does the system use any trusted execution environments in this whole architecture?
No, there is no
what if there's a malware on the device, on the architectures that you showed, and which can fake the inputs? And
yeah,
all that
exactly.
stuff?
So that's the whole idea about keeping this trusted device code base as small as possible. So what you can do is that you can implement these on a small microcontroller using ADA's PERC, which are formally verifiable. And of course, you can use some kind of countermeasure in order to harden the small hardware. But you need to trust this hardware, of course. So that's one of the trust model. But you can design the hardware in a way to make sure the attack surface is very small. Of course, having a malware on the device is, I would say, order of magnitude lower probability than having a malware into your operating system or browser.
Okay, thank you.
Yeah, thanks.
Hi, great stuff. Follow-up question on previous question. So you mentioned formal verification and the size of the TCB. Did you guys consider using a microkernel that's formally verified, like SL4?
No, we actually didn't. So technically you can, so you want to use SL4 on the host or on the device?
On the device.
Yeah, sure. I mean, you can. So that's what I said. So the implementation that you saw, that's I would say very unoptimized. So think this implementation as a kind of reference design to show what path to take in order to produce a good trusted path. You could, of course, use SL4, for example. It's a really good way to do. We didn't do it. We kind of take a really small, this tiny core kernel and did it. Of course, you can do it in better way, of course.
Cool. Thank you.
Thanks.
Okay, so I have a quick question.
Yep.
I think we still have some time. So I remember maybe in your 2 slides, before, or maybe 1 slide before, I saw a number about the display FPS is 46, right? So I wonder, like, do you have situation you may require, like, the application may require higher FPS, as far as I know, like when you're playing game, you need a much higher FPS, and maybe there could be some situation, there could be an attacker to do the game cheating or like to manipulate your game. Just a quick question.
Yeah, so this frame per second, that was a kind of hardware limitation of the HDMI interceptor we are using. So we really couldn't do anything about it, but apparently you can, so there is only one HDMI interceptor you can actually buy that doesn't really work really well. We kind of make it work, which was kind of pretty tricky, but if you get a better hardware and you can actually produce this in a way that you can get, so it's a purely hardware restriction. Fundamentally, there is no limit, such limit.
Okay, no more question, then let's thank the speaker again.